slides.
Okay.
Welcome to our next spring seminar in the Department of Botany and Plant Pathology. It's my great pleasure, let's check, yes, I'm recording. It's my great pleasure to introduce today's speaker, Dr. Emerson Del Ponte. I want you all to know that Emerson is speaking live from Brazil, and it is 8 p.m. over there now, so I really hugely appreciate that he joins us that late in the day. Emerson got his degree in agronomy from the Universidade Federal de Pelotas in Brazil, and Rio do Sul in Brazil. His master's in agronomy, same place. PhD in plant pathology in a joint sandwich program with Cornell University in Gary Bergstrom's lab, where he did a little bit of an exchange, and the university I just mentioned. Then he did a postdoc at Iowa State with XB Yang, and now he's an associate professor at the University of Viçosa in Viçosa, Brazil. He is very active in many other ways too. He's also an editor-in-chief of Tropical Plant Pathology, as well as the co-founder of the Open Plant Pathology Initiatives, something that some of you graduate students might want to check out. His research focuses mostly on plant disease epidemiology, on issues like assessment of disease intensity or crop loss, modeling, assessment of predictions of disease risk, and meta-analysis, which is, I believe, what he will be talking about today. And his experimental research has focused on Fusarium head blight and Pyricularia blast of rice. And today's seminar is about meta approaches for robust epidemiological inferences in plant disease management. Emerson, the stage is all yours. Go for it.
Thank you very much, Nick, for the nice and warm introduction. Thank you all. It's really an honor to be here. And as you mentioned, it's nice to have people from other places too. And I hope this is something useful for you. It's my experience that I would like to share. As a teacher, I know it's a seminar, but I have this idea of being live in a stage in giving a seminar is like being in a class, which I'm missing too. So I think we can have questions after the seminar, right? So I can just go ahead and give the seminar. So the idea is to talk about this fancy title that Nick just mentioned. It's about robust epidemiological inferences. It's nothing else than my experience with working with the data that comes from PDM research, plant disease management research that occurs in the field. Let me start sharing before I forget that.
Yep, I was just going to mention that. We're not seeing slides yet.
Okay, can you see something?
Yes, perfect.
Okay. This is about plant disease management research, and it's about something that occurs. We know that the plant disease management research is something that occurs in the field. And as an epidemiologist myself, we know that there's a lot that we can learn by setting up experiments to test effects or monitor behavior of, for example, host genotypes or different treatments. We know that everything works in the field, and the field is expensive work, and we know that involves a lot of multidisciplinary teams like agronomy, epidemiology, phytopathometry. We need to measure disease, we need to analyze data. And there is a lot of effort that is taken by different researchers spanning from extension, plant pathologists, research, plant pathology work in great teams. And the idea of having the field work is that we have a place where we want to test and monitor effects of treatments or behavior. Like I was saying, the different genotypes, host genotypes, different cultivars. We want to evaluate strategies that are useful for managing and controlling plant diseases. This is important because it increases our knowledge base about what to do and when to apply a chemistry, for example. All the decisions that we will need to make in the real life comes from validating technology and coming up with information that we can turn that information into knowledge and to make impact, which is really come up with recommendations for technicians, for farmers and agronomists. And it's important, this work, As an epidemiologist myself, it's I must say that we need to continue with conducting field work, because it's where things happen and where we can evaluate and validate and monitoring epidemics, because we are talking about a dynamic system, something that is working, like a treatment that is working this year or last year. We know that maybe it's not going to work in the future, and we need to set up experiments in the field to keep monitoring potential shifts or changes. So it's all about decision support system to know what to do at the right time, the right place, and when and where. We need to increase the knowledge base about options that we have to use in the field, and it's about risk information. What is the risk? What's the probability of choosing a certain chemistry or a biocontrol agent, and that demands an investment, and there's a risk of not offsetting costs, for example. I need to have a system to guide me, to advise me on what to do at the right time, what are the best options. It's the knowledge base. Where does the knowledge base come from? This comes from a lot of experiments, research, PDM research conducted over several years. And the decision support system is important also because it takes into account other factors that are important locally, like the history of the crop, the history of the field, weather information, and also the most important here in terms of farmers is the money, is the economics. Because we know that some treatments, they work very well, but they are very expensive. So we need to take into account the risk of offsetting the cost, the risk of applying something that works, but there is a cost associated. So it's something that is very, I was mentioning, is expensive. It takes a lot of effort, coordinated efforts to generate a lot of raw data that comes from the field. A lot of researchers at different locations, different years, are setting up experiments to respond, to answer important questions on plant disease management. There are a lot of interests here, as some I just mentioned before. And the raw data is important to be quickly processed. This data needs to reach the target, which is the people in need for this information in the field. So the great literature reports, university reports, are something that quickly after a season, after no work every year, this information needs to come out quickly. Ideally, that information, the data from the field should quickly reach the computer. And sometimes we know that that takes a lot of time. The more complex is your network, or the bigger your network is, it becomes a little more complicated to coordinate all these efforts to quickly move the data, to mobilize the data, and to analyze and process all this data. And speaking about academic research, is important. Eventually, some of these plant disease management research will be published in peer-reviewed articles. And that's where we combine everything, the great literature, data that we obtain from researchers, and also peer-reviewed data. They accumulate as our knowledge base. That's where we look for the information to look for the best options and the best strategy to control plant diseases. How to make sense of all these available resources? We have two different approaches. The qualitative approach, which is a narrative review, peer review. We go out in the literature, we search, we go to Google Scholar, and then we make sense of this knowledge by reviewing all this knowledge available narratively. So we can say how many experiments, some treatment work or doesn't work. Or we can take another approach, which is a more quantitative one, which is related with the meta approach, the meta analysis of the data, which is simply put, meta analysis, the analysis of the data, statistics that were analyzed before in primary studies. And it's interesting because historically, meta-analysis was developed by people from medicine and psychology. They were basically working with peer-reviewed work, peer-reviewed studies. And there are some issues when we know that when we do that, there's something called publication bias, which is the tendency to publish positive results instead of negative. And quantitative meta-analysis in plant pathology, at least so far, we are reviewing all the articles in plant pathology using meta-analysis, and I found 62 papers. Among those 62, we have 55 original articles, and basically half of those papers are using non-peer-reviewed literature, are using uniform trial network data, or are using data from the gray literature, which is good because we know that there's a chance of having non-positive results. So many experiments that we say that the experiment did not work because that was not the expected effect that we wanted to see there. So we just keep that in the drawer. So that's a file drawer problem which is very known in meta-analysis. In the meta-analysis in plant pathology, just a quick recap, quick overview of the meta-analysis, which is a statistical, nothing as like in the statistical technique. As I said, the first paper was published in Hortiscience, was not a plant pathology journal, a meta-analysis by people from UC Davis. And then that was the classic meta-analysis in terms of the kind of statistical model that people applied to analyze the data. So basically, meta-analysis is something that at the end, you have a weighted average. You have your average that is weighted by the certainty that you have on that effect. So, for example, when for experiments where the standard error is high, they get a lower weight. When you calculate the analysis, you calculate the summary measure in the meta-analysis. But the first introduction of meta-analysis to plant pathologists was in one of the APS symposium in 2004. Was a symposium, I think I wasn't there, but I think there was a talk, maybe, I'm not sure. Maybe David Gent knows about that in 2004. There was a symposium on new methods, statistical methods, and there was a meta-analysis paper. I think the paper came from a talk. And so they were explaining some of the principles and giving some examples on how to fit meta-analysis models, how we can, in plant pathology, we can apply this technique. And in 2004 and 2005, then we started to see a lot of, after this year, I counted more, so 55 articles in 15 years. So in the last 6 or 7 years, we have on average 5 new papers on meta-analysis in plant pathology, which is nothing compared with medicine and psychology. I sign up this Google Alert. My Google Alert, I receive every 3 days at least 20 papers on meta-analysis in all fields of studies. But it's interesting that people are started to apply these principles, and it's important to have this notion of what meta-analysis brings in addition to the primary studies. So in this example from 2004, people from Ohio State, they were interested in studying relationships between disease intensity and mycotoxin content in wheat, and they made use of uniform network trials. So trials that were obtained from researchers, from networks, unpublished data. In 2005, Peter Ojiambo and also Harry Sherm, they put out this very nice paper on the meta-analysis testing the effect of treatments, biocontrol treatments, different strategies, on when does biocontrol work or doesn't work, which conditions, which kind of pathogen, life history of pathogens, and so on. So 2 different approaches, 2 different sources of data, and these 2 sources, they predominate in the other studies in plant pathology, so working with an uniform trial data and working with peer-reviewed, the PDM reports here, the data source used by Peter Ojiambo. And those are actually good, they represent most of the papers conducted afterwards. And the uniform network trials, I'm going to mention about that because some examples I'm going to give from my work. I work very closely with the coordinated trials in Brazil, several networks dealing with the different plant diseases. And the coordinated efforts involves not only the funding from the industry and public funding too, which is important because it's something that is the coordinated effort of researchers, not only from the industry. So industry contracts independent. We think that this will decrease the bias. It's one target, one disease. The common set of treatments, you have uniform trials. By uniform means that the same treatments are evaluated at different locations in the same year. That could be a fungicide, a biocontrol agent. Chemicals are tested not only from one industry, but from the several. Usually we have meetings, annual meetings, to decide, make a decision on what are the interests from different industries, and they support financially, which is important, but we have some people from independent researchers saying, no, we need to keep that kind of a fungicide because it's important to keep monitoring over time. And new treatments are added over the years, and some are kept because it's important to make sure that we have the ability to monitor what's happening. And disease and yield data are obtained. So the two most important variables that we need to look at, not only disease, but yield is important because we are interested. So yield is affected because disease is causing something. The objectives and outcomes of these uniform trials is to work as a rapid response and provide yearly summaries. Usually the analyses are performed within the same year. They combine trials from the same year to rank the best treatments. And then that information is important as a snapshot of what's happening in the recent years, what's happening now. And so that's the main objective of running these experiments, is to look at a snapshot. But if we look at this combination of different snapshots over time, there is a way that we can make sense of all these data over across different years, that we can learn something new. We know that what's most important is what's happening now, but by analyzing the data from the past years and setting the right questions, maybe we can learn something new. And I hope I can show you some of this work that we've been done. The cooperative trials, just to give you an example, the first uniform trial network, very organized, was the soybean rust, which started in 2004. And after that, with the big success of this network, we have soybean white mold, wheat blast, fusarium head blight, soybean target spot, leaf with blotches, and wheat powder mildew. And I'm fortunately, I've been working closely with these networks, trying to organize and try to work with them in a way that we can rapidly obtain the data and analyze. Because for some of this network, the summary of the year was taking more than 1 year or 2 years to come out, to be published, and that's not important because we want something that goes quickly, rapidly, is disseminated quickly for the target audience. And some examples from my work, I'm going to mention 4 examples. The first study was a meta-analysis of the yield loss. We were interested in studying yield loss by soybean rust. All the examples are working with the soybean rust network. Examples number 2 and number 3 is a meta-analysis of fungicide performance. We were interested in learning something new. Beyond the publication of the yearly summaries, we wanted to make sense of the data across a series of years to understand something new. And the fourth one is a fungicide profitability tool that we developed, and it's the paper actually using Monte Carlo simulation, using some information from the previous work dealing with the yield loss models, meta-analytic yield loss models, and looking at this variation on the fungicide efficacy from the trials. The meta-analysis of the relationship between crop yield and soybean rust was a paper developed, published by Felipe Dalla Lana, my master's student back in Brazil, when he was back here. And we got access to 210 trials across 57 locations, different fungicides during 9 seasons. So the idea here was to collect all this information and try to understand the relationship between severity, the disease, and yield loss. And we expect that the disease, as the disease increases, the yield is going to reduce or decrease at a certain rate. And we are interested in determining, quantifying that rate of decline. And here, as you can see, this spaghetti plot shows a lot of one individual trial. You can see the variation in the slopes in the middle graph, and the variation on the intercepts in this left plot here. And I have a distribution. We can see a nice normal distribution for the intercepts and a distribution for the slopes here. But what the meta-analysis gave us was the average coefficient, what we can call the damage coefficient. So by knowing a damage coefficient, we can do a lot of different things. We can estimate future losses. We can predict how much yield is lost for each unitary increase in percent severity. And we are not only interested in meta-analysis. It's not only interesting to know the average or the means and the mean effect. It's important to explore the heterogeneity or the variability of the effects, why we have this variation. And that's more interesting actually in meta-analysis than the average effect. For the case of this study, we found that the damage coefficient was a little bit different. Most negative was more negative, meaning higher damage if the disease was found in the field before flowering, which makes sense. So the early onset of the disease, that means a higher damage to the crop, because this disease causes a reduction in the photosynthesis and defoliation also. And the earliest the disease occurs, the earlier it occurs, the higher the damage. And this was reflected here in the differences in the slopes of the relationship. The conclusion of this example number 1 is that yes, yield loss can be predicted from disease data, and the damage coefficient was significantly affected by disease onset time. So we can have a very simple, and that disease intensity was just I'm not sure I mentioned that, it's a critical point model, which means we assess the disease at one time only. It's the final assessment of the disease. It's not, we don't need a disease progress curve, or we don't need anything complicated, just one assessment of the disease at the R7 stage of soybean crop. The second example is a different approach. Here is we were interested in estimating the average, quantifying the effects of different fungicides. By that time, more than 7 years ago, people were applying testing in the field single active ingredient fungicides, and they were comparing with dual premixes. Most of them a combination of DMI and QI, strobilurins and triazoles. And the idea was to estimate, get this average estimate, and also not only that, because we knew by that time, based on the newest trial, which fungicides were working, but we were interested in exploring the variation, because we know that there's a lot of variation in fungicide efficacy across the country, and when we compare different locations in different years, for the same location, depending on the year, we could see clearly this variation, and we wanted to quantify the mean effect in order to rank the fungicides, but also to understand the variation across the fungicides. So as expected, the dual premixes worked much better than the single active ingredient ones. And there was a variation among the dual mixtures as well, as you can see here. So the dual premixes were on average, they were working better. But if you look at individual plots, and we use this approach called meta regression, we regressed the control efficacy against time, year, and we can see this decline. So for tebuconazole, for example, was the first one, the first report of decline of fungicides. We could see in some locations, as you can see here. Let me use this, okay. As you can see here, the first time we started to see low efficacy, and this was declining over the next years. So that means something was happening, and maybe there were resistant genotypes spreading to different locations and then reflecting in a loss of efficacy over time. And we could have a way to quantify how much is lost in terms of efficacy for every year of use of that certain fungicide. And we did this for all the fungicides, for 8 fungicides. And it's interesting, the variation within the same year. So in some locations, the fungicides are working okay. In some other locations, they are not working as expected. So we could have this kind of a plot here relating the annual reduction in the control efficacy. So the higher reduction for tebuconazole and azoxystrobin for the single active ingredient, and also the decline in the yield response in percentage points. And trifloxystrobin and prothioconazole was the only one tested during 4 years that did not decline the efficacy significantly by that time. And so the conclusion number 2 from this example was that the dual premixes outperformed all single active ingredient, and only one premix did not decline efficacy over time. All of them, that average that we estimated over 10 years was reflecting just the average, but we know that during the last year, the efficacy was a little bit lower than the average, because of this effect, clear effect of a year. So the intensive use of fungicides over time, making the population adapting to the fungicide and making the population more resistant to the fungicides. A follow-up study was conducted by my other PhD student, Jonathan Barro. It was a follow-up. In Brazil, let me tell you a story about the management for soybean rust. The first, the single active ingredient, and then the dual premix, and then the triple one with the inclusion of SDHI, the carboxamides. And we were interested in applying the same meta-analytic approach to understand, to measure, to quantify the mean effect, and also explore the effect of time, of years of use on the mean effect, on the mean efficacy. We compared the two different triple mixture, the bixafen, the one with the SDHI, and prothioconazole and trifloxystrobin, and another one here. And also we compared it with the several dual premixes, including not only the DMI and the QI, but also some of the dual premixes excluding the DMIs. We wanted to know if they were working as well as the triple premixes, because we knew that before in advance. So we wanted to check whether they were performing okay over the years. This is an exploratory plot showing that yes, every time we use a fungicide, we get less disease compared to the untreated plot. But look at this variation, it's pretty high. In some locations, still applying fungicides, we get a lot of disease, over 50% severity in many cases. When we compared the northwest of Brazil and the southeast, we did not see much differences in terms, because we have the disease occurring evenly in the two regions. And this is, over time, we did not see much differences in terms of disease. So that's the interesting table to look at, is that when we compare the same fungicides that we compared that were studied in the Dalalana study in some years before until the year 14. 4 years later, there was a decline. So we can see that interval, the 95 interval here, 81 to 85, and here from 69 to 74, there was a decline that we did not detect that decline by that time, but after the continuing use of the fungicide, we could detect that. And also for picoxystrobin and cyproconazole, we also notice a decline over time, which was repeating. So the same behavior happened again, the intensive use of a fungicide affecting the performance. And it's interesting when we look at these values for the control efficacy, the triple mixtures, they work very well, but the dual premixes that did not include any DMI was also worked okay. So it seems that the problem is with the DMIs, as you can see, except the prothioconazole. And we know that this is a highly effective fungicide and was later introduced in the field compared to the other DMIs that we have here. So here's what we had. So the dual premixes involving that includes the DMIs, the efficacy is low, and the response in terms of yield is lowest too. And we have a group of triple mixtures and the dual mixtures not including the DMIs working okay. So the champion here is this triple mixture that includes prothioconazole and bixafen as an SDHI. Looking at the best one that's interesting in terms of meta-analysis that we can explore, making sense of a lot of data, that we have some regional effects, as you can see here, for bixafen and trifloxystrobin and prothioconazole. We could see a significant difference when we compare the central western Brazil with the southeast of Brazil. And also the same occurred for some other dual premixes. The difference is significant effects depending on the region. So the map shows a lot of more red dots here, meaning that the efficacy was lower. It's generally lower in the West, and we know why, because they apply much more fungicides there. The environmental pressure for the disease is usually high, and that's where actually the first reports of resistance to the fungicides were made in the past because of the very intensive use of fungicides. And here's another plot showing the same thing for another premix. I'm going to skip that. And that's what happens in terms of the triple premix that includes the prothioconazole. We did not see any evidence of decline over time. Was the only fungicide that did not decline over time here. And picoxystrobin and benzovindiflupir shows some decline here. So it seems that all the fungicide, all the options, if we use a single active ingredient, whether a single, dual, or premix, there will be something happening in the population and quickly adapting to the fungicide, accepting some of these fungicides. The number 3, so the conclusion here is that the dual premix is declining after 4 years. The dual premixes are okay, except some of them, they are declining, but they are doing a better job, the ones that did not include the DMIs. But the triple premix and a dual with the prothioconazole is still good. Okay, let's move to the last one. The last one is the profitability work that we try to make sense of this, the two previous information, the two previous knowledge that we had about the relationship between the disease and yield, and trying to come up with a system that can help us to know what is the probability of making profit if we have, in a scenarios that we have variable disease, variable efficacy. We know that we are not certain about the efficacy, but the efficacy we know that cannot be so high. And that's because we want to maybe save in terms of a fungicide use. If we apply more fungicides, we spend more money, so it's more costly, but we expect to have a higher efficacy. And the idea here was to simulate, give to the farmers some a simulation model to play with. What if I have a certain efficacy and I have certain cost for the fungicide, what's the probability of making profit? Let me try to explain this to you. Let's start with this one here. It's a Monte Carlo simulation approach that we've developed here. It was a work by Kaique Alves, my PhD student. He came up with this very nice idea. It took me time to understand that, so I hope I learned that. Try to explain to you. So the break-even probability is the benefit is greater or equal than your cost, given a certain efficacy. So if I have a certain efficacy, like 70–80% of efficacy, which is a good one, so what's the probability of making profit depending on the application costs? So I want to be in this blue and green area here. So 8 times in 10 is 80% of the chance of breaking even here. So for that case, for 80% of efficacy, I should not spend more. I can save in terms of fungicide, no more than 45. So if I spend more than $45, I start to enter in an area where I'm approaching 50% chance. Okay, that's the idea here. So how we calculate that? We start with the efficacy. We know that the severity is strongly associated with the yield. So if we are able to reduce the severity, we are capable of saving yield. So we did some calculations here using probability distributions. So we can sample slopes. Every time we have a simulation, we sample a slope from the probability distributions that we have for the slopes, for the intercept, and for the disease in the check. And then we can have a value of fungicide efficacy. Every time I do that, for a certain efficacy, I'm going to have a different value. And I do this thousands and thousands of times, and that's the probability. I multiply the yield gain that I have here by the soybean price, which is also comes from a distribution. So I sample a price that was a price established during the last 5 years. So that's what happens here. So by doing this several times, we came out with this matrix. So that's the final product here. That's the final result. We have a matrix where we can say, well, the efficacy of the program is low. So that means maybe I'm gonna use something that I know it's based on a warning system, for example. I don't expect to have a very high efficacy, but the cost is gonna be lower. So that's the probability. I should not spend more than a certain amount of money to be capable of making profit. That's the idea. I hope I can understand better. There is an app, a shiny app I'm going to show. Let me show you something that we did. That was the simulation that Kaique produced this plot based on the simulations. And here's the observation when we related the efficacy with the yield response from the empirical relationship. It's quite similar. That means we are making sense of the epidemiological knowledge and producing something that is mimicking what's happening in the field when we have variation in terms of efficacy and in terms of yield response to the fungicide use. Let me show you this app in the website. Hope you can see my screen. Can you see my screen? Okay. Internet is a little bit slow. It's a shiny app, so we can play with a lot of different scenarios here. For example, I have the idea is to set all the situations here. So disease pressure. If I have a warning system, for example, for the season, saying, well, the disease pressure is going to be high, the next season, I can choose high severity here. The attainable yield, what is the attainable yield expected? It's high, okay, it's a good year. I expect to have, although we know that for soybean rust, if it's a good year for the soybeans, also a good year for rust. So it's gonna be a good season in terms of high yield, but also high disease. And we can set up the control efficacy here. Okay, we can define the efficacy is not so high, it's 56%, and that gives me the probability, so I can play with the total spray cost. So to reach a good probability higher than 80, for example, my total spray cost should be lower than 120. Okay, what happens here if I increase the control efficacy? If I increase the control efficacy, I can spend a little bit more in terms of fungicide. Still, the probability is going to be higher than 0.8, and I can also play with the soybean price. So if the soybean price is good, anything I do here is going to be okay, right? If the soybean is paying the price, let's just apply fungicides. Whatever you use in terms of low efficacy, it's going to be working okay. So even the cheapest fungicide or any fungicide you choose here, you have differences. That's what the app does. So it's meant to be a tool for helping with the decisions. So the conclusion number 3 is that a decision tool for making profit with the fungicides taking epidemiological, disease control, and economic factors into account. So we try to combine information that we extracted from the data from the field networks of trials using meta approaches to combine to make this kind of robust epidemiological inferences. With that, I'd like to thank my students, the guys who do all the work. I do only the talk. And that's the famous saying by Van der Planck: the chemical industry and plant breeding have forged fine tactical weapons, but only epidemiology sets the strategy. Van der Planck, thank you very much.
Thank you very much, Emerson, for a wonderful seminar. I'm sure you're hearing the thunderous applause in the background. Everybody is here thanking you for a great seminar. With that, I'll open the floor for questions.
Hi, Emerson. Thanks again for staying late and presenting the seminar to us. So I had a question on, so there's DMI resistance in the soybean rust fungus.
Yes.
Were the DMI used as not in premixes in the early years of soybean rust, or were
as a solo ingredient, basically, and also in the dual premixes, they have been used as a solo ingredient, solo fungicide. In the first years because of the price and stuff. It was working okay. If we look at the first studies done in the past in 2004, 5, 6, it was working wonderfully. But after a few years, it did not work. We started to decrease.
And is there variation within the group 3 fungicides for sensitivity? Do you see some that are still adequately control the disease?
Which ones you mean?
Within the DMIs, is there variation among the specific DMIs for resistance?
Yeah, I think based on the results I just showed you, the prothioconazole is the one that it's working okay. Basically, for all of them, they are declining over time. They are not used as a solo ingredient, as a premix, but we also have evidence that strobilurins are also losing efficacy over time. Yeah.
So would there be a premix of DMIs that would take advantage of like the negative cross resistance between individual DMIs?
I think so. There is a study showing the cross resistance. I'm not sure about who they are, but yes. But for soybean rust is interesting because if you look at the latest example I just gave you, all the premixes using DMIs, they are not working okay. So what people are actually doing now, I did not show, but I have some data. Also, we are working with that data, is the inclusion of protectant fungicides. So now it's not only the triple mixture, it's a triple mixture amended with mancozeb. It's 4 fungicides actually.
Right.
That's what is doing the job in the field. And it's a complicated issue, Dave.
Sure.
Very complicated. And because we have these, it's a huge area soybean planting. They plant soybean in Bolivia, also in some other countries, and we have an influx of spores coming every year. It's complicated. And the only thing, although I'm very optimistic, I'm not so optimistic about people using that tool. I know that it's important for science, it's important for it's an academic work, and I hope that's going to be useful. But for soybean rust, for example, everything is calendar-based. It's although it's funny because during the last years there was a huge shift in terms of soybean sowing time, the planting time, and a shift towards the use of short maturing cultivars. And I played with logistic models, just using some simulations, very simple ones. And just by doing that, just shifting planting dates and using a short cycle cultivar that reduces the cycle of soybean from the earliest from 140 days to 90 days, that makes a lot of difference. So it's a disease that is taken as a very dangerous one, because we know that it's very dangerous. And although it's not severe every year, but people have this sense that it's a very, very dangerous disease. So they take all the precautions and they spray preventatively. And it's complicated because there's not only soybean rust now. In the past was the only disease they were concerned about. But now there's a lot of other foliar diseases that we know that why they emerged because of the intensive use of fungicides. So yeah.
Thank you.
Okay.
Are there any other questions? If not, I have a couple of questions for you. So it seems to me that your standardized uniform trials probably change a little bit across years, and what experiments, what fungicides are being used, or maybe even the cultivars change, or maybe some of the treatments change too. Maybe you don't spray as often, or you spray.
Yeah.
How do you correct for that effect in your meta-analysis?
Yeah, they are uniform within the same year, that I should say. They are uniform within the same year, the same season, but they shift, they change, there are changes. What we do is that we select some of the fungicides where we monitor the effect on a certain number of trials, for example, 20 or 25. We set a minimum number of trials. So there is a lot of more than 4 or 5 fungicides, but we kind of select some that are still important in the field, and for some of them that we have information from a certain minimum number of years, location years.
Right.
And yeah, in terms of cultivars, usually it's the most susceptible one. For soybean rust, I don't think it's actually interesting because it's not planted in the same time as the commercial field. It's planted a little bit lower to get the chance of getting spores late in the season. It's not the same, and we know it's an experiment, it's a small plot, but it's the uniform, there is standardization in terms of plant disease assessment also by different people. But yes, the fungicide, what we do in the analysis, in the meta-analysis, we use this kind of network meta-analysis. We combine all the evidence from the direct evidence and the indirect evidences when we compare head-to-head fungicides. Head-to-head.
Right. Then a similar kind of question about adjusting the effect size do you adjust your observations for how much disease was in a given year in a given region on your controls or anything like that? Or is that like a covariate, or do you scale by it or anything like that?
Yes, yes, we actually do that. It's interesting because when we test, we want to quantify the yield response. For example, we wanted to know whether the yield response is higher when there is more disease or less disease in the. So we kind of do this subgroup analysis. We classify in trials with a low disease, like a baseline, with low disease as the baseline or high disease as the baseline. And there are some studies in meta-analysis showing that, in fact, if you have a low disease, the yield response is not that great, because you know that for some diseases, you should have more than a certain amount of disease to have the damage. And I think there was a meta-analysis work by Pierce-Poe in corn diseases. They clearly showed that you should have certain amount of disease to be profitable to apply fungicides, for example. So meta-analysis is nice because you can gain this, you have this power to deal with a lot of different experiments, something that it's quite difficult when you have small independent experiments analyzing individually. You can't do that using a few trials, but you certainly can do using a lot of different trials.
So I also have another more philosophical question. We all grew up doing single field trials, right? We do a randomized complete block trial with 6 replications and 10 treatments, and we compare fungicide applications to our controls that get nothing if we can't afford to do that. And then we do this 2 or 3 years, and then we publish a paper and say, you know, this fungicide works better than the other fungicide. But looking at your data across your hundreds of trials across 10 years, there is so much variability in there. Can we even trust a single study?
There is a lot. Yeah. What does a single study tell us? What does a single study tell? Yes. Yeah, I think it's a kind of a philosophical question. I think it's a good opportunity that we have to rethink this kind of work. I would love to see a kind of a structure or a database where we could deposit all these fungicide trial data, and we could work not only, I think the data itself could be valued as an important outcome and not only a report, because we know that those reports are important as you said, as I said before, as a snapshot of what's happening at a specific location and year, but we know that that's going to vary next year in other places. And ideally, it would be nice to have a database organized for certain networks that we could solve another problem that I think happens not only in Brazil, but in the US, is this time lag, the time that it takes to get the data from the researcher, organize it in a way that we can analyze and process that. Yeah. Because there are a lot of different Excel files, different formats. People like to make beauty Excel files, and it's a nightmare when we want to process. And that's why we need PhD students. They have 1 year just to organize the data, right? 2 years just to get things in place.
Just by way of background, Emerson, we had lots of discussions on the APS publications board about using the plant disease management reports and forcing authors to electronically submit the raw data with metadata that can be machine harvested for really rapid analysis.
Yeah.
And setting up the data format and the database and all of that is not something APS can do on the side, but it would be really nice. And I wrote a grant with others, including Pierce-Poe, and we didn't get it funded. It's kind of tough to get that kind of stuff funded.
Oh, really?
But I think it would be crucial to have it.
Yeah, that would be. I think we have the technology to do that. It's not complicated, but I think the complication is that we need to change the mentality of the people generating the data, and we need to kind of change what we value as an outcome. from research and extension work in plant disease management. And as long as we start to change that, I think people will see that as a good thing, and maybe the society is going to be interested in that, because we know, look at how beautiful it would be to have all this data flowing in real time to the central database, and you have a lot of different apps producing real-time plots and sending reports and email messages, and epidemiologists would benefit a lot just from having access to all this data too. So that's what epidemiologists we do. We harvest data from different locations and field, try to make sense of this data. That would be amazing. This initiative.
The example I give about this is asking Alexa or Siri, which is the best fungicide in my county right now for controlling a disease on a crop, right? Which maybe we can do in 20 years, but right now we can't even do it manually.
Yeah, that's right.
Are there any other questions?
Okay.
Any other questions? Maybe I'll stop the recording at this point and we can chat a little bit more.
Mm-hmm.